Research published in June 2025 by the USDA Agricultural Research Service confirmed what commercial beekeepers across North America had been observing for 2 seasons. In all affected colonies sampled from 6 major commercial operations, the Varroa mites tested positive for a genetic marker linked to resistance to Amitraz, the miticide that is served as the last reliable chemical option since fluvalinate and coumaphos became largely ineffective in the 1990s and 2000s, respectively. The 2026 American Bee Research Conference proceedings are equally direct. Amitraz alone is an insufficient miticide strategy. The resistance chain is now complete. Fluvalinate, the first widely adopted synthetic miticide, began failing within a decade of widespread use. Coumaphos followed the same trajectory. Amitraz was supposed to be different. It targets a different receptor pathway. It had been in use for decades before resistance appeared, and commercial beekeepers had treated it as a long-term solution rather than a temporary one. It was not different in the way that mattered. Every synthetic miticide creates a selection pressure. Every selection pressure, given sufficient time and population scale, produces resistance. The brood break protocol that 1930s beekeepers used to manage the tracheal mite crisis does not create a selection pressure. It removes the brood cells that Varroa requires to reproduce. And a Varroa population cannot evolve resistance to the absence of something it requires for survival. That distinction between a chemical target and a biological constraint is the reason the brood break method cannot follow Amitraz, coumaphos, and fluvalinate into obsolescence. This video breaks down exactly why. To understand why chemical resistance is inevitable, and why the brood break is immune to it, the underlying mechanism of resistance development needs to be precise. When Amitraz is applied to a colony, it kills the majority of Varroa mites by disrupting their octopamine and tyramine receptor function, the signaling pathway that regulates the mites' feeding, movement, and reproduction. In a large Varroa population, natural genetic variation means that a small fraction of individual mites carry mutations that reduce the sensitivity of these receptors to Amitraz. These mites survive the treatment. They reproduce. Their offspring inherit the resistance mutation. With each treatment cycle, the sensitive mites are eliminated and the resistant fraction grows. This is not an exceptional biological event. It is standard Darwinian selection operating exactly as it should. The critical point is that this mechanism requires only 2 conditions: a chemical that targets a specific biological pathway, and a population large enough and genetically variable enough to contain individuals for whom that pathway is already modified. Varroa populations in managed apiaries are enormous, undergo many reproductive cycles per season, and exist across millions of colonies worldwide. Both conditions are permanently met. Any synthetic miticide introduced into this system will, given sufficient use, produce resistant populations. This is not a probability. It is a biological certainty determined by the same evolutionary principles that produced Varroa's original host-jumping capacity from Apis cerana to Apis mellifera. The resistance timeline for each miticide generation illustrates this progression with a consistency that should have been predictive. Fluvalinate, sold commercially as Apistan, was introduced in the late 1980s as the first synthetic pyrethroid approved for Varroa control. Within 5 years of widespread adoption, populations showing reduced efficacy were documented in Europe. Within a decade, fluvalinate resistance was widespread enough that Apistan strips produced negligible mite mortality in many commercial operations. Coumaphos, check mite, was introduced as an alternative, targeting a different receptor pathway. The same trajectory followed, slightly slower because of coumaphos's different mechanism, but structurally identical. Initial high efficacy, gradual resistance development in high exposure populations, eventual widespread failure. Amitraz was introduced against this background, with explicit recognition that its different receptor target, formamidine action on octopamine receptors rather than pyrethroid action on sodium channels, should provide a longer window before resistance appeared. And it did. The window was longer. But the June 2025 USDA data confirms that the window has now closed in the commercial operations that have relied most heavily on Amitraz. The three-generation resistance chain from fluvalinate to coumaphos to Amitraz has completed. The question for beekeeping is not whether the next synthetic miticide will also eventually produce resistance. It is how long that window will be and what management framework should exist independent of any chemical's window. The RNAi-based miticide Naroa, approved by the EPA in 2025 and by California in October of that year, represents a genuinely novel mechanism, RNA interference, targeting Varroa-specific gene expression rather than receptor binding. And early field trial data showing up to 18 weeks of efficacy is encouraging. It is not, however, immune to the resistance mechanism described in the previous section. RNA interference works by degrading specific messenger RNA sequences within the target organism, preventing the expression of genes that the mite requires for survival or reproduction. A Varroa population containing individuals with mutations in the targeted gene sequences or with alternative gene expression pathways that circumvent the RNAi mechanism would show reduced sensitivity to Naroa. Whether such mutations exist at meaningful frequency in current Varroa populations, and how quickly they would sweep through the global Varroa population under Naroa selection pressure, is genuinely unknown. The product is too new, and the resistance biology of RNAi in Varroa has not yet been characterized at scale. What is known from the broader biology of RNAi-based pest control is that resistance has developed to RNA interference in other arthropod pest species within relatively short periods of commercial deployment. Naroa may prove more durable than fluvalinate, coumaphos, or Amitraz. It is not categorically different from them in the way that matters. It creates a selection pressure on a specific Varroa biological target, and Varroa populations have the population size, genetic variability, and reproductive rate to respond to that pressure. The brood break protocol is categorically different from every synthetic miticide, and from Naroa, in the specific way that produces its resistance immunity. The protocol does not target a biological pathway in the Varroa mite. It removes the brood cells. Varroa's reproductive biology is absolutely dependent on capped brood cells. The foundress mite enters a cell before capping, lays eggs inside the sealed environment, and her mated daughters emerge with the adult bee. Without capped brood, Varroa cannot reproduce at all. Not at a reduced rate, not with lower efficiency. Not at all. This absolute dependency is not a receptor function or a gene expression pathway. It is a behavioral and physiological requirement built into the deepest structure of the mite's life history. For Varroa to develop resistance to the brood break, a Varroa population would need to evolve the capacity to reproduce outside capped brood cells, to complete its reproductive cycle on adult bees, on hive surfaces, or in some other substrate that persists in a broodless colony. This is not a gradual genetic shift like receptor binding affinity reduction. It would require a fundamental reorganization of the mite's entire reproductive biology, comparable to a mammal evolving to reproduce without a uterus. Natural selection can produce remarkable biological changes over evolutionary time. It cannot produce this change in the generations available during a beekeeping management window, in response to seasonal brood breaks, because the fitness gradient required to select for extra brood reproduction in Varroa does not exist in any currently known Varroa population. The 1930s tracheal mite context in which the brood break protocol was developed and refined provides a historical anchoring that is worth examining precisely because it demonstrates that the protocol's effectiveness does not depend on Varroa-specific biology. Acarapus woodi, the tracheal mite that devastated North American and British apiaries in the 1920s and 1930s, is a completely different parasite from Varroa. It infests the respiratory trachea of adult bees rather than reproducing in capped brood. The brood break mechanism against tracheal mites operated through the adult bee population age structure rather than through brood cell elimination. Aged bees develop sclerotized tracheal tubes that the mite cannot enter. So a brood break that shifts the colony's age distribution toward older bees reduces tracheal mite transfer rates. Yet the underlying management philosophy, a colony-level biological manipulation that disrupts the parasite's population dynamics without creating a chemical selection pressure, is identical. The Ohio and Pennsylvania commercial producers who refined the brood break protocol between 1928 and 1938 were solving a different problem than the one Varroa presents. But the principle they embedded in the protocol, that a parasite dependent on specific biological conditions can be managed by controlling those conditions rather than by applying chemical toxins, is the principle that produces resistance-proof management. A chemical kills the mite that is present. A biological management removes the condition that allows the mite to persist. The second approach does not accumulate a resistance debt. The first one always does, because the selection pressure it applies is the mechanism by which resistance develops. The practical brood break protocol, the specific sequence that the 1930s producers documented and that applies directly to Varroa management today, was described in detail in the previous brood break video in this series. The core mechanism. The queen is removed to a nucleus. The parent colony is left queenless. The existing capped brood emerges over the following 10 to 14 days as the mite population shifts entirely to the phoretic phase on adult bees, and a single oxalic acid treatment applied during the broodless window achieves 95% or greater mite knockdown because every mite in the colony is accessible on an adult bee rather than protected inside a sealed cell. The replacement queen resumes laying into a colony at near zero mite load. What the Amitraz resistance data of 2025 adds to this established protocol is a specific and urgent framing. In apiaries where Amitraz is now failing to produce adequate mite knockdown, the standard post-flow treatment window is no longer producing the threshold reduction required to protect the winter bee cohort. Beekeepers who relied on Amitraz through the 2024 season and found their treatments underperforming were not experiencing application errors. They were experiencing the resistance curve that fluvalinate and Coumaphos users experienced a generation earlier. The brood break is the management option that remains fully effective regardless of which point on that resistance curve the local Varroa population has reached. Not because it is a better treatment, but because it is not a treatment at all. It is a management of conditions. The oxalic acid component of the brood break protocol deserves specific attention in the Amitraz resistance context, because oxalic acid's resistance profile is fundamentally different from that of the synthetic miticides. Oxalic acid is an organic acid that kills Varroa through direct contact toxicity. The acidic environment disrupts the mite's cuticle and physiological function when the acid contacts the mite's body surface. This is a physical mechanism rather than a receptor binding mechanism, and resistance to physical toxicity is significantly harder to develop than resistance to receptor binding toxicity because it requires structural changes to the cuticle itself rather than point mutations in a receptor gene. After more than 3 decades of oxalic acid use in European apiaries, where it was approved well before North American regulatory acceptance, no clinically significant resistance to oxalic acid in Varroa has been documented. This does not mean oxalic acid resistance is impossible. It means that the mechanism of resistance is sufficiently difficult that the Varroa population has not produced it at scale, despite extensive selection pressure. The brood break amplifies oxalic acid's effectiveness not by changing the acid's mechanism, but by ensuring that 100% of the mite population is exposed simultaneously during the broodless window. The standard objection to oxalic acid, that it cannot reach mites protected inside sealed cells, limiting efficacy to 40 to 60% in a brood-present colony, is eliminated entirely by the brood break. The combination of the brood break's biological constraint and oxalic acid's physical mechanism produces a varroa management approach whose resistance profile is the most favorable currently available. There is a specific failure mode of the brood break protocol that becomes relevant precisely in the Amitraz resistance context. A failure mode that did not exist as a practical problem when Amitraz was working reliably as a backup. The failure mode is incomplete broodlessness. If a brood break is initiated and the queen is removed, but the oxalic acid treatment is applied before all pre-removal capped brood has emerged, a significant fraction of the mite population remains protected inside sealed cells at the moment of treatment. In a colony with a mite load of 4%, applying oxalic acid when 1/3 of the brood nest is still capped means that approximately 40 to 60% of the total mite population is inaccessible. The treatment achieves 95% knockdown of the exposed phoretic population, but the mites completing reproduction in the remaining capped cells emerge after treatment and re-establish the colony's mite load. In the Amitraz era, this incomplete brood break could be followed by an Amitraz strip to manage the emerging post-break mites. With Amitraz resistance now present in many commercial populations, the post-break mite emergence must be addressed either by extending the broodless window until all pre-break brood has emerged, typically 14 to 17 days after queen removal, or by a second oxalic acid application timed to the emergence of the last pre-break capped brood. The brood break still works. Its timing tolerance has narrowed because the chemical backup that could absorb incomplete executions is no longer reliable. The commercial-scale objection to the brood break, that colony-by-colony queen removal and management is logistically prohibitive for operations managing hundreds or thousands of colonies, is real and does not disappear because Amitraz is failing. The brood break, as described here, is most practical for hobbyist and small commercial operations, managing up to approximately 50 colonies. Large commercial operations require a different implementation framework, and the research community is actively developing approaches that can produce colony-level broodlessness at scale, including controlled queen caging systems and integrated management calendars that combine physical brood manipulation with the remaining efficacious chemical options. The 2026 American Bee Research Conference proceedings document several of these approaches in the context of evaluating alternatives to Amitraz dependence. For beekeepers managing at small to medium scale, the majority of this channel's audience, the full brood break protocol remains the most biologically complete varroa management option available. For beekeepers at larger scale, the principle of the brood break, disrupting varroa's reproductive access to brood rather than targeting the mite chemically, remains the correct management philosophy, even if the specific implementation requires adaptation to operational constraints. The queen caging partial brood break described in the previous brood break video, which produces a shorter but genuine broodless window without the replacement queen mating timeline, is a practical adaptation for operations where the full removal protocol is logistically challenging. Its efficacy during the broodless window is equivalent to the full removal protocol because the mechanism is identical. All mites phoretic, single oxalic acid treatment at maximum efficacy. The viral load dimension of the Amitraz resistance crisis adds a layer of urgency to the brood break timing argument that is separate from the mite count threshold question. The June 2025 USDA research that documented Amitraz resistance also measured viral loads in the affected colonies and found alarmingly elevated titers of deformed wing virus, sac-brood virus, and acute bee paralysis virus in colonies where mite treatment was failing. Varroa is not only a direct physiological threat to individual bees through its feeding on developing pupae, it is a vector for the RNA viruses that cause the most devastating colony-level pathology. A colony with a high mite load in July and August is not simply experiencing mite pressure on individual winter bees. It is experiencing elevated viral inoculation of every bee developing during that period, with the viral load in each pupa proportional to the number of mite-feeding events during pupal development. The fat body impairment described in the summer feeding window video is partly nutritional and partly viral. High Varroa load during winter bee development suppresses fat body vitellogenin, both through the direct feeding damage and through the immune activation costs of responding to the viral load the mite delivers. A brood break that resets the mite load before the winter bee cohort is raised reduces the viral vector pressure as well as the direct feeding pressure. The winter bee cohort raised in the first post-break brood cycle develops with lower mite load, lower viral inoculation, and more effective fat body development. The Amitraz resistance crisis makes this benefit more critical, not less, because the alternative pathway to low mite winter bee production through Amitraz treatment is now increasingly unavailable. Two errors appear consistently when beekeepers first attempt the brood break in the context of a previously Amitraz-dependent management system. The first error is treating the brood break as an emergency response rather than a scheduled management action. A brood break initiated in August, after observing that the Amitraz strips placed in July are not producing the expected mite drop, is a brood break performed 8 to 12 weeks after the optimal biological window. The winter bee cohort that should have been raised in the post-break low mite environment has already begun development under the high mite conditions that the Amitraz failure allowed to persist. The brood break at this stage can still reduce the mite load and improve the conditions for whatever remains of the winter bee production window, but it cannot undo the physiological impairment of the bees already raised under elevated mite and viral pressure. The correct timing of the brood break, late June to early July, immediately following the primary flow, does not depend on observing Amitraz failure. It is scheduled on the calendar as a proactive management action, performed before any treatment outcome is known. The second error is relying on the brood break as a single annual management action without monitoring mite load in the post-break colony through the remaining summer weeks. A brood break that resets the colony to near zero mite load in mid-July will see the mite population rebuild from any remaining foundresses through August and September. A post-break mite check in early August is not optional. It is the verification that the break achieved its intended effect and that the winter bee cohort's protective window remains intact. The broader management philosophy that the Amitraz resistance crisis forces beekeeping toward is worth naming explicitly, because it changes the fundamental relationship between the beekeeper and the mite. A chemical-dependent Varroa management system is reactive by design. Apply treatment at threshold, reduce mite load, repeat. The chemical does the work. The beekeeper's primary skill is recognizing the threshold and applying the product correctly. A brood cycle-dependent management system is prospective by design. Manage the colony's brood cycle to create the biological conditions under which Varroa cannot reproduce effectively, and use chemical treatment as a targeted supplement during the windows those biological conditions create. The beekeeper's primary skill is reading and managing the brood cycle. This is not a more technically demanding skill than chemical application. It is a different one. And it is the skill that the historical commercial beekeeping tradition, from the 1930s tracheal mite management through the queen assessment, drawn comb, and summer feeding protocols described in this series, consistently developed and applied. The resistance crisis is not a crisis for beekeepers who already understand the brood cycle. It is a crisis specifically for beekeepers whose management system was built around chemical treatment as the primary Varroa control mechanism. The brood break was not invented in response to Amitraz resistance. It was developed 90 years before Amitraz was introduced, for a different parasite, on a different biological rationale. Amitraz resistance simply returns it to the center of Varroa management, where it should have been all along. The Varroa mite population in your apiary has been accumulating selection pressure from every Amitraz application you have made in the last decade. Whether your local population has reached the resistance threshold documented in the 2025 USDA data, or whether it is still in the middle of the resistance curve that fluvalinate and Coumaphos traced before it, the trajectory is established and the endpoint is known. The brood break protocol available to you this season. Queen removal in late June, broodless window by mid-July, single oxalic acid treatment at peak phoretic phase, mite load reset before the winter bee cohort begins. Does not become less effective as your Varroa population moves along that resistance curve. It does not interact with the octopamine receptor mutations that confer Amitraz resistance. It does not interact with any genetic variant that Varroa currently carries or could plausibly develop. It removes the brood cells. The mites accumulate in the phoretic phase. The oxalic acid reaches them. The mite load resets. This is the management action the 1930s producers built into their calendar when they were managing a different mite with the same biological logic. It is the management action that the 2025 resistance data confirms is no longer optional for beekeepers whose Amitraz is failing. And it is the management action that will remain fully effective for the lifetime of every beekeeper watching this video. Because the biological constraint it exploits, Varroa's absolute dependence on capped brood for reproduction, is not a target. It is a wall. Leave a comment with whether you have observed reduced Amitraz efficacy in your apiary and what your current Varroa management approach is. And subscribe if this kind of historically grounded, biology-first beekeeping is what brought you here.